Here let us see type 2. So type 2 is the integration will be in the form of integral minus infinity to infinity p of x by q of x dx, where p of x and q of x are polynomial in x, and this integral exists if q of x does not vanish for any real x, and the second condition is degree of q of x should be greater than or equal to 2 plus degree of p of x, that is degree of q of x, that is degree in the denominator should exceeds the degree in the numerator term by 2. Okay, and here the integration is taken over the semicircle modulus of z equal to r above the real axis. That is, here we have to consider the semicircle, that is like this. If you consider this is to be the axis, x axis, y axis, and this is a semicircle, we have to consider only the upper part of the circle. Okay, so here it goes up to minus infinity to plus infinity. Okay, so this is what semicircle modulus of z is equal to r. So here if we notice the question, we have to evaluate integral minus infinity to infinity x square by x square plus 1 into x square plus 4 dx using contour integration. So contour integration means here it is a closed curve. C is the semicircle above the real axis. And then here we can, for our convenient, let us consider the given function in terms of z. So let us take f of z as z square divided by z square plus 1 into z square plus 4. So for this term we have to do the integration. Clear? That is, here we have to integrate for the real axis. That is, here we can notice the closed curve C. Closed curve C is nothing but this semicircle. Okay, and then the function f of z dz. Okay, so for this function f of z we have to find out what is the answer using contour integration. Clear? And if we notice here about the degree, okay, about the degree means second condition is q of x, degree of q of x is 4, degree of p of x is 2, so it exceeds by 2. Okay, and then first condition q of x does not vanish for real x means q of x is a denominator. If you factorize this, it will give you only complex roots. Okay, for real roots it will that is q of x does not vanish for any real x, that is for real value does not vanish, only for complex roots it vanish. Okay, so while factorizing it, definitely you'll be getting only complex roots, you won't get real roots. Now to find the singular point, we have to equate the denominator to 0. So here before that we can factor this. How to factor z square plus 1? Z square plus 1 can be written as z plus I into z minus I. Similarly, z square plus 4 can be factorized as z plus 2I into z minus 2I. Right? Or otherwise, if you want to find out, we can take z square plus 1 is equal to 0. So z square is equal to minus 1. So z is equal to plus or minus I. Similarly, if you do it for z square plus 4, we will get z square is equal to minus 4. So z is equal to plus or minus 2I. So these are the factors. So since it is a polynomial of power 4, we are having 4 factors, 4 linear factors, right? So what about the poles here or singular points here? Minus I, plus I, minus 2I and plus 2I. So out of these poles, which lies in the upper half of the z plane? Upper half of the plane is, this is the point 0. So here all are imaginary parts, there is no real part. So obviously the point lies in the y-axis, right? So minus I and minus 2I will go here below the x-axis. Only we have to consider plus I and plus 2I. So this will be I, clear, and this will be 2I. Clear? This is the point 0, 2, and this is the point 0, 1, like this. So out of these 4 points, only z is equal to I and 2I lies inside the semicircle C. Okay, so we have to find out the residue only for these points I and 2I. So here residue at the point z equal to I and at the point z equal to 2I we have to find out. So both are simple pole. So we can have the formula as z minus I into the given function. Given function f of z is z square by, here it is z plus I into z minus I, and here z square plus 4. We no need to factorize this because anyway we are going to cancel only these two terms. Okay, now directly substitute z is equal to what I here. So if you put z is equal to I, we will be getting the answer here. Before that we can find the residue of this also. So here z minus 2I, again here what we can do, z square by this we can write it as z square plus 1, but here we can factorize it as z plus 2I and z minus 2I because we need to cancel this term. Clear? So now what will be the answer here? Let it be R1, let it be R2. So what is the answer here? Here finally in place of z we have to put z equal to I. Similarly here in place of z we have to put z equal to 2I. If you put, the final answer is R1 will be minus 1 by 6I. This you can verify by yourself. You can do the simplification. Finally you can check whether you are getting this value as R1 and R2. R2 is 1 by 3I. Clear? Now according to Cauchy residue theorem, what we know, integral over C f of z dz is equal to 2 pi I into sum of residue. Sum of all residue means here R1 and R2, only two residues are here. So the answer will be 2 pi I, here 1 by minus 1 by 6I plus 1 by 3I. Clear? So this is equal to 2 pi I into, we have to simplify that. If you simplify that, you'll be getting here as minus 1 plus 2 divided by 6I. So this is equal to what? Plus 1, and then here we can cancel it. It becomes 3, and here we can cancel it. So 2 minus 1 is 1, so 1, and then here it is pi, so pi divided by 3. So pi by 3 is the final answer.